Just to introduce myself, my name is John Phillips. I'm a principal product manager in EC2. I've been in the company for about 3 years, which makes me tenured for how quickly we're growing. It's great to see everyone here. It's really exciting to see the crowd, and thank you for attending. You all have a lot of curiosity about EC2, and it makes sense because often EC2 performance is critical for the performance of your applications. And so today we're going to talk to you about how EC2 instances deliver system performance. Whenever I talk about EC2, I start by saying EC2 is big. And it's not just because we've got an incredible scale. We've got a global scale, and we have data centers all over the world. But it's because there's just a lot to learn about EC2. And you could have deep dives on a number of topics. One of them is how you purchase EC2 instances. So you could go into Spot, and there's some great sessions this week on Spot. You could go into reserved instances. You could get into our new offering, dedicated hosts. And of course, there's on-demand. And so there's a lot to learn there. There's a lot to learn about our networking. So you've got VPC, and you've got a ton of VPC features. And there's some great networking talks this week and that are good for deep diving into that area. There are also our APIs and the ways that you interact with EC2 instances. So the commands that you use to launch and set up your instances, the AMIs themselves, you've got auto-scaling, CloudFormation, and all those things are really awesome to know too. And the analogy I like to draw between all of these and the virtual machines themselves are that the APIs and the other ways to actually purchase and get set up are like getting in the car and turning the key and turning the ignition. And that the virtual machine performance itself is like driving the car. So virtual machine performance is like driving the car. This session's about driving the car. And again, our instances are sitting in data centers all over the world, and they're in hardware. They're on hardware with hypervisors, and the virtual machines sit on top of that. And over time, we've greatly expanded the breadth of our offering. So we started back in 2006, and we had one instance. It didn't have a name back then, but it's actually came to be the M1 Small. It had one vCPU and 1.7 gigabytes of memory. And since I've joined back in 2012, it's crazy to think about how much we've done. We've greatly expanded the offering, and there are two reasons for that. One of them is that we've introduced new families. We now have a bunch of instance families, or 5 instance families, general purpose, compute optimized, storage optimized, memory optimized, GPUs. And then within each family, we've started to turn out generations. So we use generations to deliver new features and performance that are relevant to a particular instance family. And we've recently introduced D2, C4, and M4 as current generations in the storage optimized, general purpose, and compute optimized families. And so we've got a ton to choose from, and it's really, in understanding the performances each is really important for understanding which one to choose. So what to expect? So we're going to first take some time to define system performance and why it's so important. And then we're going to get into how Amazon EC2 instances deliver instance performance in a virtualized world. And then along the way, give you some tips and some tricks how to make the most out of your experience. Because once you know you're making the most out of your instance experience, then you can focus on selecting the right instance and making the right instance selection for your workload. So defining performance. In order to improve performance, the first step is to actually define what it is and figure out how to measure it. And I like to talk about how servers are hired to do jobs. And what that job is really depends on what your business objectives are or what your personal objectives are, what the application is doing. And so if you try to generalize, there are a few things to think about, a few ways to describe performance. One is response time. How quickly can you do a unit of work, however you define what that unit is. Throughput is, how much of a work per unit of time can you get done. And then often consistency is really, really important. So paying attention not just to what the performance is in response time or throughput, but also how consistently you get that performance. And how you define performance really depends on your perspective. So if you're looking at a database application, when you issue the query, how quickly does it come back? How many queries per second can you run? How many transactions per second can you do? When it's a web application, you're talking about request response time. How many requests per second can you run? If you're doing machine learning inferences, how many inferences can you do per unit of time? And then when you move down the stack, getting closer to the virtual machine itself, you'll consider things like file system performance. Are you getting cache hits on your file system cache and statistics in your buffer? And then once you get down to the device level, you're talking about CPU, memory, disk I/O, network I/O, and how those resources are utilized and saturated. And how efficiently those resources are utilized directly impacts your application's performance. A simple thread state model for understanding that is really your application is either on the CPU in user mode and executing, or it's not. And if it's not, it can be doing a number of things. It can be waiting on the CPU to get scheduled. It could be waiting for disk or network I/O. It could be waiting for memory to page in, or it could just be idle. But again, it's a simple model for simply saying that your workload performance depends on the resources that support it and how efficiently they're utilized. And so when we think about instances, we think about CPU, memory, the network interface, and disk. And some of the key factors there are, for CPU, for example, number of sockets, number of cores, the power of those cores, the clock frequency, the bursting capability, and then the key indicator that you'll notice when you run some of your performance monitoring tools are CPU utilization and run queue length. For memory, you care a lot about memory capacity, and the key indicators there are how much free memory you have. And if you don't have free memory, you'll often see anonymous paging or swapping to disk. That's a sign that you're memory bottlenecked. When you're talking about network, you look at the max bandwidth that your network interface can produce, its packet rate, and you're considering receive and transmit throughput over that capability as how fully that resource is utilized. And with disks, you've got input-output operations per second, or IOPS, and throughput. And again, the device can get saturated, so you may have a wait queue length, and you're looking at device utilization and also device errors. And so your application can get bottlenecked on any one of these things, and getting the most out of each of the resources is important, so you can first understand where the bottlenecks are, and then so you can choose the right instance type. And the key lesson there is that for something that's 100% utilized, adding, it can't accept any more work, and you need to focus on that bottleneck in order to improve your application's performance. And it's actually interesting because you don't necessarily need to see 100% utilization of something. When you're measuring and you're considering minutely averages or 5-minute averages or something like that, you could see an average of 60, 70, 80% utilization and actually still be bottlenecking on that resource, because when you look at the smaller time intervals, you're getting up to 100%. And so just to make this a little more real, we set up a web application. It's a 2-server architecture, a client server, and we had the client drive load onto a MediaWiki installation running on Apache with 140 pages. We did a little bit of optimizing. We did PHP ops code caching, and we did some file system caching to try to reduce the overhead. And then over time, we drove load. So we used Siege, and then we used cPanel on the server, or sorry, not cPanel. We used collectd on the server to do monitoring, and the monitoring collected at 10-second intervals, so we got a pretty good idea of what resources were being used, and it hooked into Apache so we could see what requests per second were being driven. And this chart shows that I upped requests per second over time. And just a quick note about monitoring. Monitoring is really important, and we offer a bunch of CloudWatch statistics to help you with that. But it's really a shared effort because we intentionally can't see everything that's going on inside your instance. So it's very helpful to use tools There's some great partners that we have that provide tools, and we have open source, and there are open source tools out there for collecting statistics on what's going on in your servers. In this particular case, we first took a look at memory statistics, and this is an M4 large, and so it has 8 gigs of memory, and we have plenty of free memory. So we look at it, and we're pretty happy that we're not, if you go look at the swapping too, we're not doing any swapping or anonymous paging, so we're pretty happy that there's enough memory on the host. Then we went and looked at disk stats, and this is attached to an EBS GP2 volume, our general purpose SSD volume. And you can see from the charts that we're not driving a ton of IOPS. It's actually all writes. So you can see that our file system cache is actually working pretty well. All the reads are getting caught. And the bytes being transferred is pretty small. And so just from the drive, from the EBS performance definition, we know that we're actually not hitting a bottleneck there. And then we look at network stats. You've got packets per second, and you've got bytes transferred. And again, you can see the load increasing over time like we would expect, but we're driving a really low number of packets per second receive and transmit, and then we're not saturating our network. So we finally looked at CPU utilization, and it's broken down in pretty good granularity. We see that this is actually where we're approaching our bottleneck. And it just happens to be, if you did a cursory installation of MediaWiki, this is what happens, but the chart's broken down into 2 categories. One is the user mode CPU utilization, and the other is system. And system is the time that your kernel spends executing system calls. And so your application's not on the CPU, it's been context switched out, but the kernel's executing privileged instructions. So it's really important to understand this because instance selection on EC2 is a tantamount to performance tuning. And it's really pretty incredible. It used to be that if you bought a server, you spent a lot of money up front, you waited a long time to get it, and then you really, really, really needed to make it work for whatever you had in mind. And it can be a stressful process to make it work if there's a lot of risk involved and a lot of money up front. And with EC2, you can try out an instance and give it back just as easily as you launched it and experiment with a new configuration and find out the one that's best suited for your workload. Okay, so we talked about why it's so important to understand workload performance, and we talked about how you can look at resource utilization of your EC2 instance. And so the question is, that's all interesting, and you know, maybe we knew that already, but how do you actually give me compute performance? How do you actually give me I/O performance in a virtualized world? I kind of get it on bare metal, but when you're virtualized, how does that happen? Virtualization being key to what we do here because it's critical to being able to spin up instances quickly. It's critical to being able to give them back. So it really gives you that agility that comes with EC2. So we're first going to talk about how we deliver compute performance. So as I kind of pointed out earlier, there are 2 predominant types of CPU utilization. One was system calls in kernel mode, and the other was user mode. And x86 64 CPUs have at least 2 protection levels. And on bare metal, they're used to, the lowest or the most privileged level is used to execute privileged instructions on the CPU, which change the state of the system. These can be anything from changing memory mappings to requesting I/O to timekeeping. And it's to protect the system from applications. And so when you want to layer on virtualization and you want to actually virtualize the machine, the question is, where do you put the virtual machine manager? Where do you put the hypervisor so that it can then enforce those same kind of protections for the system, but at a layer below the kernel of the operating system in the guest virtual machine? And just to make it a little more, but first just to make it a little more concrete what we're talking about when we say privileged instructions. I used a command strace on the same web application to let us know what types of system calls are being used most frequently, where we're spending the most time. So why does system call performance matter? Why does privileged instruction performance matter? And in this particular case, where we're reading a bunch of wiki pages, you can see that there are a lot of file operations. You've got reads, writes, opens and closes, and stats and file stats. So that's pretty expected, but the performance of those particular instructions will be important to an application as you look at your CPU utilization chart and you see the system performance consuming a greater majority of the CPU than what we have for this application. Okay, so system call performance is important. Prior to Intel VTX, which is a hardware virtualization technology, you still had the two protection modes on the CPU, and you had to figure out how is a virtual machine going to trap privileged instructions and moderate the execution of those instructions. And way back in the day, there were really two options. There was one option for that, and when it all first started, and that was binary translation. And so it was the virtual machine, or the VMM job, or the hypervisor's job to actually scan the instruction stream to detect when there was a privileged instruction and then handle it. That's a very expensive process. But the upside of that was that you really didn't need to modify the guest operating system. What came next was paravirtualization, which offered a simplified device model, and it basically ignored a bunch of stuff. It said, okay, for privileged instructions that the most privileged mode or the hypervisor can't trap right away, we're just going to ignore them, but we're going to have to tell the operating system and the guest to replace them with hypercalls, which were to replace some system calls. You also had paravirtualized extensions to replace some device emulation because there was network devices and disk devices that were very expensive to emulate. But even with paravirtualization in a two-ring structure like this, system calls or hypercalls had to go through the virtual machine manager and added latency. And so what you would see is system call performance suffer. So what's next? Hardware virtualization. So this is after Intel VTX. This created another privilege level in the CPU for the hypervisor to sit. And this meant that you could get down to the most privileged ring very quickly for certain instructions. And then in fact, you could get really great performance on system calls without having to modify the guest operating system. This is what all the current generation Amazon EC2 instances have today. And so this is a great new way that provided a lot of flexibility in the guest to kind of launch whatever operating system you needed to. But you still had some devices to emulate that were very expensive to do. Network devices are very complicated, and to fully emulate them actually required a lot of work and could slow down your network performance, or same thing for disks. And so what happened was we would use paravirtualized extensions opportunistically to improve performance where it was necessary. And so we did that for network and block I/O, and we're actually going to talk a little bit more about that later. But the result is a virtualization spectrum, where on the one hand you've got a modified operating system, and on the other hand you've got an unmodified, and then sort of in the middle is the best performance, where you've got a PV HVM system that gives you the best performance. And that's what we call our HVM AMIs. And so we offer a couple of AMI types, Amazon Machine Image types. One is PV, and the other is HVM, which is actually PV HVM. It's hardware virtualized with the paravirtualized extensions for network and disk I/O. And the important thing to remember here, just the tip to take home, is use HVM AMIs. And this is just a picture of the Amazon Linux detail page where we talk about all the different options that you have. And you can still launch PV-backed AMIs, but you really want to use hardware virtualization with the paravirtualized drivers for network and disk I/O, and that's the HVM AMI. Speaking of system calls, and before we close out this topic, one pretty important one that it's helpful to talk about is actually get time of day or query performance counter. It's the calls that you'll make to actually get time. And it can be really impactful for a couple of reasons. One is you might be doing debugging or JVM tracing or something like that, and it's really critical that you get really high performance access to time so that you can do debugging. And then the other thing is that you want to make sure it's very accurate, so you don't get unstable time can cause all kinds of problems. And so you've got a couple options on EC2 today, and you can actually query the available clock sources to see what your options are. Zen has a paravirtualized timer. There's the TSC, and there are a few other options. And the important thing about the model in virtualization is that the operating system is actually querying for time rather than getting events for time. If it were to use purely to use timer interrupts, but it was scheduled off of a vCPU, and we'll talk about how you can schedule instances on and off of CPUs, then it could have a distorted view of time. And so we query clock sources, and the tip here is actually to use TSC. It's a CPU counter. It's accessible from user space with some help, and all of our current generation instances support TSC as a clock source. And here's an example in Linux of how you can go change it. You can query your available clock sources, and then you can look at your current clock source. You can use a text editor of your choice to change the grub configuration and the kernel line to use a different clock source. Okay, so that's system call performance. Now, what about just the hypervisors? One of its key jobs is to schedule CPU so that make sure every instance gets CPU time. If you're using HVM AMEs, now the question is like, okay, so I know what to do there. I know how to get the best system call performance. Now, how do I understand when I launch an instance how it actually gets CPU scheduled by the hypervisor? There are a couple ways to do that. And I've labeled them in two categories. One is a fixed allocation, which essentially means that you're given a constant allocation of CPU. That can be done in a couple of ways. One is you get dedicated access to cores. There's a direct relationship between your instance virtual CPUs and the underlying cores, and you get the cores whether or not you need them. And that's the uncapped version of it. The capped version of it is when you give a fixed allocation, but it's enforced by the hypervisor scheduler, and it can actually put a cap on the virtual CPU so you can get a fraction of the underlying cores. There's other scheduling that's often done, or at least as an option, and it doesn't pertain to EC2 instances, but it's interesting to look at. Variable allocation can result in variable performance. And the motivations for doing something like that, if you see variable performance, is that there's often the goal of work conservation. So it's a provider that's looking to maximize their CPU utilization rather than give a predictable experience. And there are a couple of different schedulers you can do that. And one of the ways is fairness schedulers or share schedulers, so that when the box is used up, you can give virtual machines priority on the CPU. Another would be a deadline or response time scheduler, where the idea is that, say you're getting web requests, you want to make sure the virtual machines that are getting web requests on your system are being handled quickly. And so the deadline scheduler just ensures that the CPU gets, the virtual CPUs are scheduled on the physical CPUs quickly. Okay, but in EC2, we provide fixed allocations. And one of the examples where we do that, and we do a kind of a direct relationship between cores and vCPUs. You get them whenever, even if you're not using them, is C4. And it's really C4, M4, D2, all of the current generation instances. And the really cool thing about doing that is it enables you to do a couple of things. It enables really predictable performance and consistent performance. And it also enables us to give finer grained controls over the underlying cores because they're yours. C4 instances is when we first released something called P and C state controls, which allows you to control the sleep and the power states of the underlying Intel CPU. And you can do that with the C4 8 extra large, which is our largest size. And C4 is the fastest EC2 instance out there. So why would you want to do that? Well, what's interesting about being able to control the C and P states is that if you put all the cores in a deeper idle state, that creates the thermal headroom for you to actually turbo up or put into a higher power state a single core so that you can get up to 300 megahertz higher clock frequency. And so if you're really tinkering around with performance and you have an application that would benefit from really high single thread performance, you can do that. The trade-off is that to wake those idle cores up is that you incur a little bit of variability. And so if your application isn't tolerant of variability, you can that you might not want to do this, and you could actually lock everything into a consistent power state. To make it a little more concrete about when this is useful is if you've got an application like a transcoding application that leverages AVX2. AVX2 is a very power-hungry instruction. And so when you run it, it actually takes all the cores down into a lower power state. And if you don't preset the processor down into the cores down into the lower power state, you can actually cause you can cause some variability. And again, if your workload is variability sensitive, you may not want to do that. Okay, so with C4 instances, you get fixed allocations, you get the cores, they're yours. With T2 instances, we introduced something I think is really cool, and that is fixed allocations of CPU enforced with CPU credits. When we created T2, we basically responded to feedback that, hey, I know my application needs a bunch of memory, I know how much memory it needs, but I often find that the CPU is idle. Now, we wanted to figure out a way to give customers an instance that had less CPU without doing a hard cap on the amount of CPU you get, so that essentially, when you use the CPU, you get the full core as if you're running on a C3 or a C4, for instance, but you're limited into how long you can do that. And it's been a really effective way for customers to take applications that don't need a ton of CPU, and they can operate within their credit balance and just have incredible performance for a fraction of the cost. And so here's the lineup with T2. We recently launched the T2 Large. Out of response to customer feedback, it's got 8 gigs of RAM and 2 vCPUs. And I'll take a little bit of time to explain the credit model and then relate it back down to the hypervisor and how this is actually enforced. So that you could think about the credit model for T2 instances as a credit bucket. They continuously receive credits over time, and they actually start with a pretty hefty balance when you first launch a T2 instance. So when you start up, you're running at full speed. An instance consumes credits when it's scheduled onto the CPU. In other words, when your application needs to use the CPU, it's scheduled on, and it deducts from your credit balance. The other thing is that the credits expire or leak after 24 hours. This model allows us to ensure that you're getting a fixed amount of performance over a period of time. And if you happen to need more, that's great. You can actually use a T2 larger size, a larger T2 size, or another instance type. Okay, so this is a new model for delivering CPU. How do you keep track of it? The tip is to actually look at some of the new unique CloudWatch metrics that are specific to T2, and that's the CPU credit balance and the CPU credit usage. So you can actually, the hypervisor keeps track of all this stuff, and then we throw it into CloudWatch so that you can see how much CPU credit your T2 instances have. So between C4 and T2 as examples, you've got a couple of ways that we can deliver virtual machine performance through the hypervisor. What about monitoring performance? And before we close out the CPU topic, I just wanted to talk about monitoring performance. So we looked at the charts earlier, and we saw that a couple of indicators of work that's being done. You've got user time, you've got system time, and you've got I/O wait time, for example. Else, you may not even be using the CPU. But what happens if the virtual machine manager or the hypervisor schedules you off the CPU? For example, when you run out of T2 credits. So you're normally getting the full core performance on T2, and you ran out of credits, so now you're being throttled to the rate at which you receive credits. That actually shows up as something called steal time. And a common misconception with steal time is that it's actually hurting your workload's performance. You see it, you wonder what it is, and you think, gosh, I'm having performance that's stolen from me. And it's actually more appropriately labeled something like involuntarily scheduled off the CPU. And in the case of T2, which uses a CPU cap to enforce the CPU credit balance of 0, that happens. At millisecond intervals, at a time slice, you're actually scheduled off the CPU so that you're actually operating at a rate once you're out of CPU credits, which is consistent with the rate at which you earn the credits, or what we call baseline performance. So the key here is to leverage CloudWatch metrics, keep track of your CPU credit balances, And there are also a couple other edge cases where the hypervisor is doing work, and you might see little blips of seal time, but the key, again, is to remember that it's not actually impacting your instance performance. And in the case of T2, it's part of the product definition, the CPU credit product definition. Okay, so we talked about how the virtual machine schedules instances on and off CPUs and how we deliver that. What about I/O? Your workload performance is often, very dependent on I/O performance, whether it's disk I/O or network I/O. How does that work? Well, it's the hypervisors, it's the virtualization and the hypervisor's job to schedule I/O requests between virtual machines and shared physical devices. And there are a couple ways to do that. One common way is the pair virtualized network and disk driver model way, which is called the split driver model. And I'll spend some time talking a little bit more about that. After Intel introduced a feature called Intel VTD, which introduced an I/O memory management unit, you can actually also do direct device pass-through of an I/O device or an accelerator directly to the instances, and so you avoid any of the I/O scheduling by the hypervisor altogether. So first, the split driver model. This is a depiction of how it kind of works. You've got the hardware layer with all the physical resources. You've got the virtual machine manager layer. And then you've got the guest domains and then something called the driver domain. The driver domain has the actual physical device drivers in it and what we call the back-end network or block device driver. The back-end network or block device driver communicates with a front-end driver that sits in the guest operating systems. And this is a simplified version of a driver, and it doesn't require any expensive emulation on the part of the hypervisor or in the driver domain. So how did the back end and front end drivers actually communicate with each other? We'll find out that actually matters a lot because you can employ some kernels and pay attention to some things that allow you to get much better performance in the split driver model. So there are really three things that make the split driver model work. One is a communication ring buffer, which is a shared memory page between the guest domain and the I/O domain. And that's where the guest domain will put in operations and commands. It'll say, I want to do a read, I want to do a write. And the other part of it is an event notification system called event channels, where after the guest, for example, says, I want to do a read, it rings the doorbell to the driver domain and says, do this read for me. And then the final part of it is a memory granting system so that when the I/O is ready, so if the driver domain, for example, grabs the information it needs from the disk, pulls it into memory, that memory is actually granted and shared with the guest so that it can then go pull the data back in for use by the application. So three things: a communication ring buffer, an event channel notification system, and then a mechanism for granting shared memory between the two domains so that you can transfer lots of data. So that seems kind of complicated and involves a lot of steps. I'll walk you through those steps, but the key here is that any inefficiencies in this process are going to show up when you're doing a lot of I/O. And we've got an instance that is capable of doing a lot of I/O, and that is as I2 instances. So when we launched it, we marketed it as being able to do 365K random read IOPS. And that's just a ton of I/O, an insane amount. And it's a really awesome instance type. And I often joke that if you don't know what instance to use, you can start with an I2 8 extra large and then work it down from there. So how do you actually get 365,000 read IOPS? Here's the process that I just described. And so the chart, the blocks on the right are the guest virtual memory, and then you have the virtual memory of the I/O domain. And the steps are that the instance actually grants memory to the I/O domain, and it does so through a hypercall to the virtual machine manager. It writes the commands it wants, the operations it wants to execute to the communication ring buffer. It signals to the driver domain that it wants to go read the ring buffer and actually do what it needs to do. And then the driver domain maps those grants, performs the operation, copies the data into the grants, and then signals back to the instance. And it unmaps the grants, the memory pages that have been granted. And this is actually expensive because in the process of mapping and unmapping granted pages, the system incurs TLB flushes, and those can be expensive. And so what you'll see in pre-3.8.0 kernels is that you're not actually able to achieve the rated performance of an i2 8 extra large, the 365K IOPS. You actually need to use a kernel that supports persistent and indirect grants. And the difference in the process here is that the mapping and unmapping doesn't happen. The I/O domain and the guest domain pre-agree on a shared grant pool, which in other words is the granted pages. And instead of doing all the mapping and unmapping, the guest just copies to and from the grant pool. And so if you're using 3.8.0 kernel or greater, you actually benefit from this performance improvement. You can drive the 365K read IOPS that we discussed for the i2 8 extra large. And to be more concrete, you can use Amazon Linux 13.09 or later, Ubuntu 14.04 or later, and RHEL 7 or later to take advantage of this feature. So one thing that we talked about in the process of explaining the split driver model is event handling. So there's a notification system so that the guest can ring the doorbell of the driver domain and vice versa. And you could think about events as interrupts. A virtual CPU has to get preempted and handle the callbacks. And that can be expensive if you're doing a ton of I/O or getting a ton of notifications. And if you're in the proximity of 100,000 to 200,000 notifications, and they're all being handled by a single virtual CPU on the guest, it can actually overwhelm that CPU, and you can see reduced CPU performance. So there was an early kernel version, 2.6.36, where notifications went to a single virtual hardware interrupt. And beyond that, you had support for event callbacks in Zen, which allows the hypervisor to, or lets the instance tell the hypervisor to which vCPUs to target with event notifications. And you can actually see that this is enabled and that you're more evenly distributing event notifications across vCPUs by checking dmessage and looking for the text Zen HVM callback vector for event deliveries enabled. And you can actually look in Linux at your interrupts and interrupt counts over time and ensure that they're evenly distributed over vCPUs, and that's an important performance improvement. IRQ balance is another package that helps distribute interrupts, and it supports Zen event callbacks in version 1.07 or higher. So in addition to using the modern kernels, you just want to make sure that the modern kernels get you a lot. And so using the modern kernels are really helpful for doing I/O in a virtualized environment. And then IRQ balancing is also important. So that was disk. Now on to networking. So a lot of what we talked about for disk I/O also applies to network I/O. You've got the split driver model with front-end drivers and back-end drivers. The device driver sits in the driver domain and communicates with the physical NIC. And so this is just a quick illustration of a packet going through into the front-end driver, the back-end driver, copied. Essentially what happened here is the guest wrote into a communication ring buffer, signaled to the driver domain. It read from the communication ring buffer the pages it was granted with the data it needs and what to do with it, and then sends the data out through the physical NIC. Well, what if you could just avoid all of this? What if you could directly pass through a network device to the instance and avoid all of this traversing? And you can. We introduced enhanced networking a little while ago, and it uses single root I/O virtualization to expose a physical network device through a virtual function to an instance. And this means you completely disintermediate the driver domain. You don't, in this particular case, you're using a specialized driver and you don't need to worry about persistent grants for network I/O performance. And you can get a ton higher IOPS because you've got a physical device that's dedicated for doing the packet processing for you. So you get lower latencies, high IOPS, and the trick is that your OS needs to know, it needs to have the right drivers installed, and EC2 needs to be told that you're using enhanced networking because we will do a configuration in the hypervisor itself that says, hey, I want you to expose the virtual networking functions to this instance versus using the split device driver model. And so after enhanced networking, you've got a different paradigm. The data goes from the application to the NIC driver within the guest, straight to the SRIOV network device. In our case, what we have today is the Intel 82599 network driver. It's included in Amazon Linux, and you can also download it and install it on your own. So the tip is to use enhanced networking. You get high IOPS, low latencies. The instance must support it. And the way that the signaling actually happens, so you signal to EC2 to use this property is through an AMI property. And so you look for that your AMIs have, and your AMIs have this property on your, I forgot what the command is, but you can look at it through the console or using the command line when you describe an AMI, and it'll say SRIOV simple if it's enabled. Okay, so we've talked a lot about the importance of understanding performance, about the importance of understanding what the resources are capable of. We've got a number of instances that have great technology under the hood. Intel CPUs, lots of fast SSDs. We've got a model for delivering CPU that allows you to pay less for it because you don't need as much, and that's T2. And you can use CPU credits instead of having CPU laying around when you don't need it. And we've talked about device pass-through and how you can get really awesome networking performance. And how the hypervisor in the virtual machine world is actually delivered. So just to recap, instance selection is tantamount to performance tuning. I can't stress this enough. Setting up definitions of performance, monitoring performance, and then making changes. You know, EC2 is awesome for that. You can give an instance back just as quickly as you got it. So like I said, you could start with an i2 8 extra large and then give it back to us as soon as you find out it's too much for what you need. But in order to start this process, you need to know that you're actually getting the most out of your EC2 instance to begin with. And so we talked about using PV-HVM AMIs. So make sure that you're taking advantage of hardware virtualization, and make sure you're taking advantage of pair-virtualized extensions where it makes sense to, and that's to use PV-HVM AMIs. Layer on to that enhanced networking drivers, and making sure your instances AMIs tell us that you're using enhanced networking, and you get the best of hardware virtualization, PV extensions, and device pass-through. Timekeeping, use the TSC. That'll give you the best performance. And when I'm talking about the different ways we deliver CPU performance, when you get the cores and the cores are dedicated to you, we can offer things like finer control over them. And so you've got C-state and P-state control, which is really cool if you're getting into tuning for specific workloads, for example, workloads that use AVX2. Monitor your T2 CPU credits. T2s are a really awesome option. I talk to customers, particularly big customers that have a big IT organization, but they want to give their developers flexibility and agility. So they let their developers go and launch a bunch of instances. Well, you actually don't want them launching i2 8 extra larges if you're concerned about cost first. And T2 is a terrific default if you're trying to govern your organization to experiment with instances and have them start with T2. Use modern kernel versions to take advantage of persistent grants for I/O performance. This makes a huge difference. When you're running a benchmark, you can see a 50% to 80 to 90% performance difference on IOPS if you've got persistent grants versus not using persistent grants. And then remember that event callbacks need to be distributed across guest virtual CPUs. And if you're seeing one vCPU pegged really high, and you check where the interrupts are being delivered, they're all being delivered to that vCPU in a high I/O situation, for example, you can look at distributing those IRQs better. And that's, again, making sure you're using modern kernel versions and also making sure you're using IRQ balancing tools. And then, again, use enhanced networking. So really appreciate you guys being here. I'm glad that we could talk a little bit more about how we deliver virtualized performance, and I hope you can take these tips home. If you didn't hear something that you wanted to hear, we've got a lot in the EC2 documentation, but we've also got a bunch of our engineers here around the developer booth, and I'll be available outside right after this to answer any of your questions. So thank you very much.